Hello everyone, my name is Arya Gupta and I will be giving a presentation on the paper Extending Lattice Linearity for Self-Stabilizing Algorithms. In this presentation, first we will introduce the problems that we have addressed in this paper. We will provide with an example algorithm. We will discuss how that algorithm possesses the property of lattice linearity and what are the benefits behind such an extension. We will give some more example algorithms and finally we will conclude the presentation. Consider the minimal vertex cover problem. In this problem, the input is an arbitrary graph G and the desired output is a minimal set V of nodes such that for every pair of adjacent nodes, at least one of those nodes is in V. We are going to consider this example graph. It contains two nodes connected to each other by an edge. There are two possible states, in and out. If for some node the state is in, then we are going to consider that the node is in V. And if the state is out, then we are going to consider that the node is not in V. Rules for node 1 are as follows. If the state of node 1 is out and the state of node 2 is also out, then node 1 changes its state to in. And if the state of node 1 is in and the state of node 2 is also in, then node 1 changes its state to out. Rules for node 2 are same as the rules for node 1. In this slide, we are going to study what happens when the nodes perform executions under algorithm 1 in an interleaving fashion. If we look at global state 1, node 1 is in the vertex cover. We have a vertex cover. So this is a feasible state. This state is also an optimal state because we cannot remove node 1 from the vertex cover. Otherwise, we will not have a vertex cover. Similarly, global state 2 is also an optimal and a feasible state. Global state 3 is a feasible state because we have a vertex cover. It is not an optimal state because we can remove one of these nodes from the vertex cover and we will still have a vertex cover. Global state 4 is not an optimal state and it is also not a feasible state because we do not have a vertex cover. Now let's study global state 3. If node 1 is allowed to perform execution first, then state 3 transitions to state 2. If node 2 is allowed to perform execution first, state 3 transitions to state 1. Similarly, we can make observations in state 4 and we are guaranteeing convergence in this case. Let's see what happens when the nodes do not perform execution in an interleaving fashion. Let's assume that in state 3, both the nodes read the states of each other at the same time. Node 1 will read that the edge is covered, and even if node 1 moves out, the edge will stay covered. So node 1 will move out. Similarly, node 2 will read the same and node 2 will also move out. And the next global state will be state 4. When we are at state 4, both the nodes will read that the edge is not covered, and therefore in the next state, both the nodes will move in, and the next state will be global state 3. In such cases, it may happen that we obtain a sequence of infinite states where state 3 and state 4 are present at alternating positions, and the graph may never converge. It may never reach an optimal state. So we have seen that algorithm 1 converges with interleaving executions. It may also converge with central scheduler. It may also converge when the nodes use locks while performing executions, but it may not converge if the scheduler chooses more than one nodes to perform execution simultaneously. Let's step back and generalize algorithm 1 for general graphs. We have two macros to do that. A node I is removable if and only if every edge that contains I shall be covered, even if I changes its state to out. And a node I is unsatisfied if and only if there is at least one edge which contains I and is not covered. Algorithm 2 is a generalization of algorithm 1 for general graphs, where if a node is removable, that node changes its state to out, and if a node I is unsatisfied, then I changes its state to in. Now, how do we fix this problem? What we want to do is we want to move to a feasible state as soon as possible. So we are going to allow state 4 to transition to state 1, state 2, or state 3. But we do not want, while we are in a feasible state, we do not want to leave, we do not want to violate the feasibility of the state. So we do not want to move from state 3 to go back to state 4. And therefore, we have to put some restrictions here. We have the restrictions that we have put is that we only allow node 2 to move out before node 1, and therefore we do not move back from state 3 to state 4. State 3 also does not transition to state 2. State 3 only transitions to state 1. What we are doing here is we have declared node 2 as a forbidden node in global state 3, and therefore node 2 will move out before node 1. Node 1 has to wait for node 2. It has to allow node 2 to move out first. Let's generalize the notion of a node being forbidden. A node I is forbidden if it satisfies the three conditions. The state of I should be in, I should be removable, and for every node j which is adjacent to I, j should not be removable, and if j is removable, then the ID of j should be less than the ID of I. If the node I is forbidden, then what we want to do is only then we want to allow I to change its state to out. Our algorithm is put as algorithm 3 for general graphs. We want to move to a feasible state as soon as possible, and so we do not change the second rule, where if a node I is unsatisfied, I changes its state to in. But we do not want I to move to a move out of the vertex cover as soon as it realizes that it is removable. But we only want to do that when I is forbidden. So we have changed rule 1, where if a node is forbidden, then it changes its state to out. If we apply algorithm 3 to any of these states, state 4 is allowed to transition to state 1, state 2, or state 3 based on which nodes are allowed to perform execution in which order. But state 3 is only allowed to transition to state 1, and therefore we guarantee convergence. We can make some observations about algorithm 3. If at the beginning of some round V is not feasible, then by the end of that round, V will be feasible. This is because when every node is allowed to perform execution, as soon as an unsatisfied node realizes its position, it changes its state to in. The second observation is if at some move, V is feasible but not optimal, then by the next move, at least exactly one node will leave the vertex cover. This is because since the vertex cover is feasible, none of the nodes will be unsatisfied. But since the vertex cover is not optimal, there will be some nodes which will be removable. And since all the IDs are distinct, at least one of the nodes will be forbidden. And as the forbidden node leaves the vertex cover, the size of the vertex cover will reduce by 1. Third observation is if at some time step V is optimal, then V remains the same. This is because the nodes which are in the vertex cover, they are not removable, because otherwise this will violate the feasibility of the vertex cover. And the nodes which are out of the vertex cover, they are already satisfied, so they don't have to move in. This slide gives a little hint about the application of lattice linearity in algorithm 3. In the 2 example node, we have deemed node 2 to be the forbidden node because node 2 is of a higher ID. Node 1 has to wait for node 2 and allow node 2 to move out first. Only after node 2 moves out, node 1 can re-evaluate its guards and compute whether it is forbidden or not. Because of this, even if nodes are reading old values, algorithm 3 is guaranteed to converge. Lattice linearity has been discussed earlier in a paper by Vijay Garg. The task was to find a predicate which represents a problem as the lattice of states. The states can only transition in one direction. They can either transition upwards or downwards throughout the execution of the algorithm. There can be 2 or more feasible solutions, but only one state is the optimal solution. Because of such a structure, we have the following observation. If a system does not satisfy the predicate, then there will be at least one node which is forbidden. That node has to change its state in order to have G satisfy the predicate, otherwise G will never satisfy the predicate. This slide demonstrates our motivation behind the extension of lattice linearity to algorithms. Let us study global state 3 again. If we allow state 3 to transition to state 2, we are allowing node 1 to be forbidden. If we allow node state 3 to transition to state 1, we are allowing node 2 to be forbidden. But both the nodes cannot be forbidden. And also, if both the nodes are forbidden, then state 3 is can be allowed to move to state 4 as well, which we do not want to do. In fact, vertex cover problem, the minimal vertex cover problem is not a lattice linear problem. It does not possess a lattice linear predicate. There are more than one optimal states possible in the vertex cover problem for general graphs. Our algorithm is divided into 2 phases. The first phase is aggressively entering the feasible state, where every node, as soon as it realizes that it is unsatisfied, it turns itself into the vertex cover. As the graph enters a feasible state, it enters a lattice of states. The optimal states are present at the top of the lattice. And when the graph enters a feasible state, the algorithm starts behaving lattice linearly, where only selective nodes are allowed to leave the vertex cover. Only the forbidden nodes are allowed to leave the vertex cover. Because of such a structure, we have the following observation. If the graph is not in an optimal state, then there must exist at least one node which is forbidden. That node has to change its state in order for G to satisfy, to reach the optimal state. Otherwise, G will never enter an optimal state. We call such algorithms eventually lattice linear self-stabilizing algorithms. Benefits of using such algorithms are as follows. We do not have to require nodes to run in lockstep. Nodes can perform executions without any requirement of synchronization. Nodes can perform execution in read-write model. And we can allow nodes to rely on old data, and even after that, convergence of algorithms is guaranteed. We have studied a few more problems from the perspective of eventually lattice linear self-stabilizing algorithms. One of these problems is service demand-based dominating set problem. This problem is a generalization of the dominating set problem. In this problem, the notion of a node I being unsatisfied or a node I being removable can be defined trivially. Let's discuss the definition of a node I being forbidden, and it has to satisfy 3 conditions to be forbidden. The state of I should be in, I should be removable, and for every node k, which is commonly dominating some node along with I, k should not be removable Or if k is removable, then the ID of k should be less than the ID of I. The algorithm can be defined as follows. If I is forbidden, then I changes its state to out. And if I is unsatisfied, then I changes its state to in. We have also studied the maximal independent set problem. This problem is different than the other two problems. In the other problems, we have tried to compute a minimal set, whereas in this problem, we will compute a maximal set. And that is the reason that we have replaced the notion of a node being removable to the notion of a node being addable. A node I being addable is defined as follows. For every node j in the adjacency of I, the state of j should be out. We are going to define the notion of I being forbidden formally. And again, we have three conditions for that. The state of I should be out. I should be addable. And for every node j in the adjacency of I, j should not be addable. And if j is addable, then the ID of j should be less than the ID of I. The algorithm can be defined as follows. If I is forbidden, then I changes its state to in. And if I is unsatisfied, then I changes its state to out. We have also studied the graph coloring problem. This problem is a little different than the other three problems. This is because in the other three problems, the domain of states of nodes is a binary domain. You have only two states in and out. Whereas in this problem, the domain of states of nodes can be as large as the set of natural numbers. So in this problem, the notion of a node I being forbidden can be defined again by three conditions. I should be unsatisfied. I should not be unsatisfied, which means that I should not have a conflicting color with any of its neighbors. I should be subtractable. It means that there should be a color value less than the color value of I, which I can obtain without any conflict with any of its neighbors. And the third condition is, for every node j in the adjacency of I, j should not be subtractable. And if j is subtractable, then the ID of j should be less than the ID of I. Rules for the algorithm for graph coloring can be defined as follows. If a node I is forbidden, then the color I changes its color value to the minimum available color value. And if a node I is unsatisfied, then I adds its ID value to its color value. As conclusion, we can observe the following points. In general, it is desired for a system to reach a feasible state as soon as possible, and our algorithms are able to achieve this property. The algorithms that we have defined, they allow nodes to perform executions with any level of concurrency. They also allow nodes to perform executions in read-write model. These algorithms can be converted into fully lattice linear algorithms, where in addition to being selective to enter an optimal state, we have to be selective while entering feasible state as well. And here we will give priority to the nodes with lower ID. We call such algorithms lattice linear self-stabilizing algorithms. As future work, it might be interesting to study if we can implement approximation algorithms under the paradigms of lattice linear and eventually lattice linear self-stabilizing algorithms. It might also be interesting to study exactly what class of problems can be solved under these paradigms. This concludes my presentation. Thank you.